All right, so the first thing is the first quiz is a week from today. So that must be the 12th. And so that's just going to be the last 5 or 10 minutes of class, just maybe 6-ish short answer questions, just making sure that you're reading and trying to make sense out of the notes. It's not going to be any calculations or anything. It's just about like remembering what I say in class. Okay? Any questions about the quiz? We're going to do a lot of quizzes, so each one isn't worth a ton of points or anything like that. But and then did I assign? I don't know if I assigned first law number 5. I think I only assigned the first 2, didn't I? Oh, 1 through 5.
Intro 7 to 8, and then first law 1 through 5.
Okay.
That's what the announcement.
Okay, great. Let's see. Come on. God dang it. What is going on? This is what happens when you get old. Like, you don't know how to work anything. Okay, so the first law, number 5. So you want to see a problem like number 5, but not that particular one, or you want me to just go through number 5?
Well, I was thinking like something similar to it because like I did that one and I think I kind of understand it.
Mm-hmm.
Well, like I did use this solution every step of the way.
Okay.
I only got just finding the initial volume.
Okay.
And W equals like the integral of the starting and ending volume.
Okay, well, let's just go through number 5 and I'll just sort of talk about what I'm thinking at each step. All right, so we have a certain mass of a gas. That gas is going to be our system. That's what we're going to sort of focus on, isolate when we use the first law. It undergoes a constant pressure process. So let's see, what am I thinking so far? We know the mass. And so knowing the mass is going to let us go back and forth between specific quantities and true quantities. Like in this case, we're going to go back and forth between specific volume and the true volume. It undergoes a constant pressure process. Okay, so this is a big one. Constant pressure. One thing that means to us, we learned about this last class, is that we can use the formula, this integral formula for the work of expansion that says the work of expansion is the integral from the starting volume to the ending volume of P dV. Okay. I mean, that integral expression is always true, but we can't always use it. In order to use it, we need to have the pressure as a function of volume, or better yet, pressure constant. So this is going to make using that formula easy. That formula is really important when you're doing first law problems, because this is a way to calculate the work, and work is one of the terms in the first law. Okay, so constant pressure immediately makes me think like I'm going to use this integral, and that integral then is going to go into the first law. And that constant pressure is 5 bar. 1 bar is 1 times 10 to the 5th pascals. So I'm always going to just convert this to SI units. So this is 5 times 10 to the 5th pascals. And I'm going to think about, so the first law is always processes. So it's always going from one instant to another instant. Okay, so I'm going to think about my 2 instants. It's going to give us properties at each one of these instants. Instant 1, it says that the specific volume, so that's lowercase v, is 0.1 cubic meters per kilogram. And then instant 2, we're not given any properties. Well, we know the pressure at both of them. But we do know, we are told that 15 kilojoules of work, so 15 times 10 to the third joules of work is done on the surroundings by the gas. So now you have to think about the sign convention. If work is done on the surroundings, does that make our W positive or negative? Positive, yep. So work is equal to positive 15 times 10 to the third. And then, so now we can say the work is the integral from V1 to V2 of pressure dV. We're given that the specific volume at instant 1 is this. So the true volume is the specific volume. Well, let me write that out first. So the true volume is the specific volume times the mass. And so that's 0.1 times 0.2 kilograms. So 0.02 cubic meters. And now we can start plugging stuff in. The work is equal to the integral from 0.02 meters to the second volume. And it's the integral of the pressure, which is 5 times 10 to the 5 dV. Since that pressure is constant, you can pull that outside of the integral. So 5.0 times 10 to the 5 times the integral from 0.02 to V2 dV. And this work is equal to, I'm going to plug that in now, so 15 times 10 to the third is equal to, if you do this integral, you get 5.0 times 10 to the fifth times the quantity V2 minus 0.02. And now you can divide both sides by 5 times 10 to the fifth, and you get 0.03 is equal to V2 minus 0.02. And so V2 is 0.05 cubic meters. And this actually, it looks like this doesn't ask you to plug this into the first law. But it's pretty common in problems like this that now it would say like, okay, now you know the work. Let's say also that we know that this cylinder is insulated. What's the change in internal energy? Okay, something like that. So what if part B said the cylinder is insulated, um, what's the change in internal energy? Well, we know that the work is 15 times 10 to the third. We know that the first law says this. Okay. We're going to assume that there's no change in kinetic or potential energy because there's nothing in the question that makes you think that those would change. So we're just going to say that this is equal to the change in internal energy. Q is 0 because it's insulated. And so the change in internal energy is equal to negative 15,000 times 10 to the third, I think it was, joules. Okay. And then if you knew some things about the gas that we're isolating, you could, like we'll do later, figure out ways to determine the increase in temperature or whether it's changing phase or things like that. Okay. Any questions about that question, that problem? So one thing that this brings up is, so this says that the pressure is constant. These problems a lot of times will say, you know, the thing is, the pressure is constant, the volume is constant, the temperature is constant. So I want to give you, those are just sort of words, but let's think about how a process would happen that would hold these properties constant. Okay. So these are like the physical causes of various constant properties. Okay, the first one is constant volume. And if you want to sound fancy, you can call that isochoric. And this one's pretty intuitive. How would you keep the volume of a gas constant during a process?
Put it in a container.
Yeah, exactly. Just a fixed container. So as long as this thing happens in a fixed container, the gas is always just expanding to fill that whole container and the volume stays constant. What about constant temperature? So the fancy name for this is isothermal. And the way you would do this is you would keep the gas in thermal contact with some temperature reservoir. and you would keep the process slow. So, for example, if your cylinder had a bottom that was brass or some metal that conducted heat easily, um, and that brass was surrounded by a temperature of 20 degrees Celsius or something, and you let this process go slowly enough that the heat could transfer back and forth, then whatever you did, the gas inside that's touching that brass bottom of the cylinder would stay at 20 degrees Celsius. Okay? Can you picture what I mean with that? And then the last one is constant pressure. Um, and the other word for this is isobaric. Um, and for this, you would have gas in the cylinder. Um, and you would have a constant force applied to the top of the piston. So that means that if, so say that you, well, let's just think about it in terms of uh, a free body diagram of the piston. Um, so the piston maybe would have a weight. You'd be applying this constant additional force of F that could be a combination of some force you're applying artificially or whatever, and the pressure of the atmosphere pushing down. And then the gas pressure is P. Well, if you just let this, so constant force applied to the top of the piston, let's say let the piston move freely. Then this piston is going to find an equilibrium state no matter what happens to the gas, where that pressure inside is balancing this constant force pushing down. Okay, so like if you heat up the gas inside the cylinder, that makes the gas want to expand, and that gas will push the piston up until that equilibrium is found. And that piston will just move around to maintain that constant pressure. Okay? Any questions about that? Anybody want me to help clarify how that works?
Like a pneumatic regulator, that you change the dial
Yeah.
that changes the pressure
Yeah.
and holds the pressure constant. Is that something similar to it, or how does one of those regulators work?
How does it work? I don't know. I assume it just has a valve that opens, requires a certain amount of pressure to open. And I guess that's sort of a different thing than this. But yeah, I guess so. If you just have a um, if you just have a valve on the side of your tank, that whatever pressure happens to the gas, if that pressure hits, say, 2 bar or something, then that opens the valve and just lets gas out until there's less material inside. And then the valve isn't open anymore, so then it's stuck in there. That's how that would work. So that's not what I'm describing, but that would also keep pressure constant. Any other questions? I mean, I guess you could, you could think of it being like a valve with a hole in the side and a spring holding a plunger down. And when enough force is applied by the pressure of the gas to push the plunger up above the hole, gas escapes. Can you picture what I'm talking about? So that if I was going to design one, that would be my first thought. Yeah. Uh, okay, the next thing I want to talk about is polytropic processes. And I assigned a couple problems where you had to deal with these. They're really just mathematical problems, so you can kind of fight your way through it, but I want to bring up some things that will make it a little easier. And so a polytropic process is one where the pressure times the true volume to the power of n is equal to a constant. Okay, and whenever you see a volume, you need to ask yourself, am I looking at a specific volume or a true volume? This is a true volume. For true volume, it's always going to be a capital V. And so I'm going to always indicate that with, I'll try to draw it bigger and I'll put a little serif on top. Yeah.
What is the difference between the true volume and specific?
Yeah. Well, in SI units, the true volume V that's volume. So that has units of meters cubed. Okay. The specific volume is lowercase v, and that is the volume per mass. And it has units of meters cubed over kilograms. And also remember that the specific volume is 1 over the density. So when you see V, you have to be careful. Like, do I want capital V? Do I have capital V? Or, that's always going to be an important step. We're going to use specific volume a lot. We're actually, pretty soon, we're going to start using specific volume. It's going to be more useful to us than the actual volume, the true volume. Okay, so this is an exponential thing. A lot of times you're going to have to solve for that exponent n. And so let me write down some exponent rules and stuff that'll be useful for these polytropic processes. Okay, the first one is that the natural log of some value a times some value b is equal to the natural log of a plus the natural log of b. The second one, this comes up in almost all of these kind of problems. The natural log of a to some power is equal to the power times the natural log of a. So that's going to be useful because if you're trying to solve for that exponent, this is a way to do the algebra to isolate the exponent. And then the third one is if you're given a value times another one to the nth power, like you are in that definition of a polytropic process. You can isolate A by multiplying both sides by B to the negative n power. Whoops, I didn't write this whole thing. This is supposed to be, so if you have this equal to C, like the polytropic process definition, then you can isolate A, like I said, by multiplying both sides by B to the negative n, and you get C times B to the negative n. Okay, well, let's do a couple examples. So let's say that we're given that the pressure times the volume to the power of 1.2 is equal to a constant. And we're given that at instant 1, the pressure is 3 bar, and the volume is 0.1 cubic meters. And then at instant 2, we're given that the volume is 0.2 cubic meters. So first, what's the work, W, for the process? And second, if the system is insulated, what's the change in internal energy? Okay, a lot of times in these polytropic process problems, we have to solve for the exponent. In this case, it's given. And what is a polytropic process? Like, how would you know this? This is a case where rather than basing our calculations on stuff we know about a specific substance, we or somebody has just done an experiment of the kind of process that we're doing and found that it's sort of like a curve fit. Okay, so it's just an experimental result that doesn't really take the thermodynamic properties of the substance into account. Okay, it just looks at it and says, but often processes have this form with various exponents. Okay, so just think of that, that's something that's given to you. And what about the volumes? Are those specific volumes or true volumes? Yep, that's right. And so W, what are we? So for W, we're looking for the work of expansion. And one thing so these polytropic process problems are almost going to always require you to calculate the work of expansion. And the reason for that is they allow you to come up with pressure as a function of volume. Okay, remember that's the requirement for computing that integral. So, okay, let's see what we can figure out. This pressure, it's given as 3 bar. To put it into SI units, that's 3 times 10 to the 5th pascals. And we don't know what that constant is. We want to know what it is. And we can use the pressure and volume at instant 1 to find that constant. So at instant 1, we have that 3 times 10 to the 5th times 0.1 to the power of 1.2 is equal to C. And so we can just punch that into a calculator and figure out what that constant C is. And in this case, we get 18,928.7. There are units, but since we're in SI units, we know that all the units will work out. So you would only need to use them if you want to be extra sure and check your work. I tend to just leave it off and just assume the units are working. But I guess the units would be crazy. I mean, it's units of pascals times meters to the 3.6 power. That's a very weird unit. Okay, so now that we have this C, now we want to come up with pressure as a function of volume. Okay. Well, we have this equation that says pressure times volume to the 1.2 is equal to 18,928.7. So now we can multiply both sides by V to the negative 1.2. And we get that pressure is equal to 18,928.7 V to the negative 1.2. And that's our pressure as a function of volume. And so now the work is the integral from V1, which was 0.1, to V2, which is 0.2, of 18,928.7 dV. Nope, I skipped an important part, sorry. 18,928.7. The formula is, did I write it? Work is equal to the integral from V1 to V2 of P dV. Our P is this thing I wrote above here, so I need to put in the V to the negative 1.2 and then dV. And I can pull that constant out. So 18,928.7 times the integral from 0.1 to 0.2 of V to the negative 1.2 dV. And now I can use the exponent rule for integrals. So W is equal to 18,928.7. And that integral is V to the negative 0.2, because I added 1 to the exponent, divided by negative 0.2. And we're evaluating this from 0.1 to 0.2. And so punch all these values in, and you get that the work is 19,417.4. And this is work, so the SI units are going to be energy units, joules. Let's do what we can to sanity check this answer. We got a positive value for work. Does it make sense? Do we have a way to make sense out of the fact that W is positive, or say that it should be negative or whatever? Can you think of a way to do that? Given what we know? Well, what do we know about the signs of work of expansion? If the gas expands, is work positive or negative? Positive. And if the volume decreases, the work would be negative. So this is saying that the gas expanded, and we're given the two volumes. It goes from point 1 to point 2. So that makes sense. Okay, so we feel a little better about that answer knowing that the sign was right. Any questions about that process? And then for part B, we're trying to calculate the change in internal energy. The first law says the change in energy is equal to Q minus W. There's no reason to think we have to worry about changes in kinetic or potential energy. So this is just going to be the change in internal energy. It says that the container is insulated, so there's no heat transfer. And so the change in internal energy is equal to negative 19,417.4. So negative 19,417.4 joules. And again, you could use that to calculate what you expect to be the change in temperature of the gas or something if you know some information about the gas. Any questions about that? Okay, notice one thing here. So in this problem, we had one unknown in this polytropic process equation. The only unknown was the constant. Okay? If you also don't know the exponent, that's two unknowns. So since in this example we only had one unknown, we only needed a pressure and volume at one instant to solve for that one unknown. If you also don't know the exponent, you need to be given the pressure and volume at a second instant also, two equations to solve for two unknowns. So let's do one where you have to solve for the exponent. And this time, the polytropic process equation is going to be in a little different form, but don't worry about that. That's just algebra or whatever to deal with. Instead, just think about how many variables you need to figure out the variables that show up in that equation. So during this process, let's say the pressure is equal to A times V to the power of B. And 200 joules of heat is added to the gas. And what we know is that at instant 1, the pressure is 2 bar and the volume is 0.3 cubic meters. And at instant 2, the pressure is 0.5 bar and the volume, hold on a sec, is 1.5 meters cubed. and we're told that there's 200 joules of heat added to the gas, so Q is equal to positive 200. Let's see. And we just want to calculate what's the change in internal energy. Okay, so in order to find the change in internal energy, we know what Q is. We're going to need to calculate the work of expansion, like we almost always are going to have to when we have these polytropic equations. And in order to do that, we need pressure as a function of volume. Okay, that means we need to solve for A and B. And so I'm going to start with my instant 1. And it says that 2 times 10 to the 5th, 2 bar, is equal to A times 0.3 to the power of B. That's one equation. We can't solve for 2 unknowns with that, but we also have the second one that says 0.5 times 10 to the 5th pascals is equal to A times 1.5 to the B. And I guess I'm going to isolate A so I can set the two sides equal. So A is equal to 2 times 10 to the 5th times 0.3 to the negative B. And this one says A is equal to 0.5 times 10 to the 5th times 1.5 to the negative B. Now I can set the two right sides equal to each other. So 2 times 10 to the 5th times 0.3 to the negative B is equal to 0.5 times 10 to the 5th times 1.5 to the negative B. And so I will make that, I'll divide both sides by 0.5 to the 5th. So that's 4 on this side. And over here, 1.5 divided by 0.3 is 5. So I have 5 to the negative B. And then I'll take natural log of 4 is equal to negative B times the natural log of 5. And so B is equal to the negative natural log of 4 over the natural log of 5.
Professor,
Yeah.
how did you get 4 equals 5 to the negative B again?
You got in 1.5 to negative B divided by 0.3 since they have the same
Right.
base.
So if you have like A to the N is equal to B to the N, and you divide both sides by B to the N, so you get this, which you can rewrite as just this.
Thank you.
Yep. Okay, so B is equal to negative 0.861. And that's what I got before. That's good. And now we have to calculate A. You can use either one of these equations. So A is equal to 2 times 10 to the fifth. Okay, 2 times 10 to the fifth times 0.3 to the power of 0.861. And you get positive 70,930.2. Okay, so now we have A and B, and we can write that the pressure is equal to 70,930.2 times V to the negative 0.861. Now we can calculate the work. So that is V1 to V2. So V1 was 0.3, V2 was 1.5, and it's the integral of PdV, so pressure is 70,930.2 times V to the negative 0.861 dV. We don't have time to go through this integral, but what you would get if you did this integral is that work is equal to 108,159 joules. Does it make sense that W is positive? Yeah, the volume increased, so the work has to be positive, and then we can say from the first law, the change in internal energy is equal to the heat transfer was positive 200. We're subtracting the work, 108,000, so that heat is pretty insignificant. And so the change in internal energy is negative 107,959 joules. And so if no phase change happened, what you would expect here is that the temperature of the gas went down. And if you knew specific characteristics of the gas, you could calculate how much the temperature went down. Any questions about that? Okay, that's all. Yes.
I had a question.
Yeah.
Is this like the same as the homework on introduction 10, 11, and 14? It looked much easier at first.
Yeah, it is.
Okay.
It is.
That was assigned
Last Friday. Okay. I really screwed you over on that one. But I mean, it is just math, so you can sort of fumble your way through. But I know of all the math you've learned, like logs and exponent stuff, is probably the stuff you use the least. So it probably takes a little refresher. But if you want to turn it in now, feel free. Yeah.
So for exam, if we can input the integral into our calculators, we have to go.
I guess that's okay.
Oh.
Yeah.